Kyle, I'm a PhD candidate at Western Sydney University and CSIRO, and today I'll be sharing a systematic review which we conducted for our project, which is analyzing software tools for energy efficiency. So some quick insights from the literature review. The biggest changes to buildings occur in concept stage of an architectural design pipeline. Current tools are often not easily integrated into concept stage. They often occur later, requiring input criteria which are often used during DA drawings. And as a result, it means results are slow. And so this review was split into 5 thematic blocks, which we identified through an industry focus group with 18 practitioners across different size firms in New South Wales. So the 5 key blocks we looked at is interoperability. Interoperability is covering how effective data or BIM files can be transferred from Revit to analysis tools such as First Rate 5 for sustainability consultants. Building energy modeling, which is for performance modeling and annual energy output. Life cycle analysis, so we're looking at tools like one-click LCA and various other LCA tools on embodied-carbon and how widely they're used in practice. Occupant behavior, we wanted to identify how different behavioral contexts can impact the findings. And then machine learning. So machine learning we looked at as a novel approach which existing tools do not use, but some pre-developed tools in the literature do highlight some of the benefits. So for interoperability, we found that translations remain fragile, and semantics go missing. So what this means when we start with data-rich formats such as BIM, and we share these to sustainability consultants, the tools they're using are often using PDF formats. And so there's a lot of data that is lost from BIM to PDF. And then because there's a remodeling in many of these tools, manual checks persist. So you're more prone to errors when there's more remodeling as opposed to just working with the IFC data. And then so this leads to problems with early iteration. So in architectural pipelines, the earlier in a stage we make changes, the greater impacts we can have to reduce carbon emissions. And so moving on, we look into the first of the 2 key types, which is building energy modeling. So this is for thermal analysis often. Tools require many inputs, and architects often don't have that inputs at early stage. So we find that workload fit drives adoption. So if tools are not often easily integrated into existing architecture pipelines, such as Revit plugins, and we found that literature shows that architectural adoption is much lower. And then interoperability is a greater issue than capability. So it's not that the algorithms don't perform well, it's that they don't fit well enough into an architect's pipeline so that they can use them in the background. And that's what we found has been a more prevalent issue than algorithms themselves. And so for LCA, there's a lot of similar issues that remain in LCA. So links are often semi-manual. So again, it's an interoperability issue when translating between software. For material mapping, LCA is obviously it's very highly dependent on the coefficients, and those coefficients are dependent on the materials which are assigned to the geometry. And in early stage, if you don't have your right materials mapped, then you can get very wildly inaccurate performance. So material mapping is one of the most important parts for LCA analysis. And again, yes, few inputs results in poor assessments. So we've noticed tools such as Autodesk Forma, which is formerly Insights. If material maps are not assigned correctly, they'll automatically be assigned a default one. And so there's a lot of a lot of manual work that still persists through the pipeline. So with results depend on the different databases. So it all depends on how each software developer has chosen to source their coefficients for carbon emissions for the materials. And so the literature shows that there is some discrepancy between different tools, and it's not 100% clear due to some tools using proprietary data. And so architects often want traceability. So if they cannot see how a tool has come to or led to the output that is given, then it's a lot more difficult for architects to willingly adopt such a tool. And so moving on to occupant behavior, it's really important to understand that context differs very, very widely. So we can have, for instance, a class 2 apartment in one state that may perform very differently in another state, or even within suburbs. And so this becomes one of the more prevalent issues which the literature shows. So again, it's not so much on algorithms, but also things like how occupants use a space, which differs a lot. So in order to model this more accurately, the data needs to be wide enough to actually represent various different contexts and various different behavioral types. And so looking into machine learning, there are recent tools such as the one from Cyro's Rapid Rate, which uses machine learning to reduce the input criteria. So ML can improve some of the, or address some of the issues which I had mentioned previously, but it's, again, very data dependent. So Rapid Rate, which is one in New South Wales, which assesses thermal output, annual thermal output from for class 2 and class 1 homes. It uses the NATHAS dataset, but even then, performance metrics are still not as accurate as a explicit physics equation. So there is evidence that ML can help, but again, it's still early stage. And so that leads on to gaps and opportunities. So this systematic review is the first part of our PhD project. And from this, we're now moving on to identify, we have identified that there's a lack of early stage tools. Most research tools do target BIM, not so much LCA, and there's even less on occupancy behavior. Current responses are slow, so architects are after something with real-time or near real-time feedback. A lot of tools are often cloud-based, and it can depend a lot depending on the amount of geometry which is in a BIM file. We could end up with maybe 20-minute responses from some of these tools. And this ends up being quite a burden in an everyday architectural practice, where the goal is to be something that can work in the back end as opposed to take up much of the architect's time. So these tools are not often integrated easily for non-technical users. So it's a different skill set and often requires a sustainability consultant to use many of these tools. So as such, this provides another opportunity for researchers to explore. And again, because of the interoperability issues and because of the fact that consultants have to remodel based off floor plans to get these tools to work, this means that there may often be geometry cleanup when moving between tools. And yes, these are all of the key gaps and opportunities which I've identified, and that's it. If anyone has any questions, feel free to ask.
Yeah, I think